Good afternoon, everyone. I am Professor Andrzej Zwilindowski, Head of School of Mathematics of Physics of University of Lincoln. I welcome you in our first lecture, Lincoln Math and Physics Week 2021. Before I start, I'll just a couple of comments. If you happen to hear a fire alarm, you need to follow regulations of your own place where you are. Second thing is we stream in live, and but a video will be recorded. You therefore will be able to watch it later on. During our session, you can ask questions directly in the chat of YouTube, and then we will try to scroll it and find all the questions. Or those who registered using Eventbrite, you received a link for anonymous question in so-called Padlet, which doesn't require a Google account. You can post also there, and after lecture, the speaker will answer those questions. Before we go to actual program, I say a few introductory words about the host school which organizes these lectures. Just a second, file is loading. So again, welcome everyone. I'm Professor Andrzej Zwilindowski, Head of School of Mathematics of Physics at the University of Lincoln. In the normal days, you would come to our public lectures in our beautiful campus at the waterfront. These days, it's everything virtual. However, we hope that when pandemic is over, you will visit us again. We are a very small city, just about 100,000 inhabitants, with a beautiful campus, but also a very beautiful city by itself. City of Lincoln is quite old. Romans conquered this territory in the 1st century, and it was place of famous 9th Legion here. The city received the prestigious status of Colonia already in times of Emperor Domitian, and some remains of Roman times can still be seen in the city, and you can walk under the Roman arch of Roman Gate. The next big step was already after William the Conqueror. The city received his famous castle and most famous cathedral, Lincoln Cathedral, which was also started in 11th century to be built, and then once was the highest building on the planet. And most importantly, it's very beautiful building. And already from Middle Ages, that was seat of learning as well. However, City of Lincoln, being so old, has very modern university, with our campus open in 1996, and again we sit on a very beautiful waterfront. That building is home of our school, Mathematics and Physics, and we very modern school, and also one of newest school in United Kingdom, opened only in 2014. And our home, Isaac Newton building, is even younger, just about 4 years old next month. And of course, our lecture series of Science Week is part of British Science Week, and they of course aimed at everyone, but specifically to those who study maths or physics in schools. And of course I'll mention that you might consider our university as well for your further study. And I just say that we School of Math and Physics, and therefore we have both of these disciplines. We have bachelor and master's degree in mathematics or in physics. We also have a connection with another Asian discipline, philosophy, and again, you can study math with philosophy or physics with philosophy. You can study other combination, like you can study together math and physics if you wish so, or math and computer science if you love computers. And with that, I finish my presentation. And now I will introduce our speaker of tonight. Just let's wait that speaker appears on the screen. Tonight, our first speaker, our first lecture of Science Weeks is Dr. Helen Christodoulidi. So now, hello, Helen.
Hi.
So, Helen received her doctorate degree, which is the highest degree in academic career from University of Patras in Greece in 2010. She worked at researcher positions in various countries, in particular in Germany, in Max Planck Institute for Physics of Complex Systems, while her PhD is in applied mathematics, so it shows how these two disciplines are connected. She also worked at research position in Italy, University of Padua, and also in her country of Greece, in famous Academy of Athens. And from 2019, Eleni joined our school as a lecturer, and now she will give us a talk about something very, very interesting in mathematics. And after this talk, you can ask questions. Again, you can put them in a chat in YouTube, or you can anonymously put in that Padlet link, which you can find in your email, which you receive from Eventbrite several times today. And now, Eleni, we welcome your talk of this afternoon.
Hello everyone, my name is Helen Christodoulidi. I am a lecturer at the University of Lincoln in the School of Mathematics and Physics, and this talk is about giving you an idea of what is mathematical modeling. So to understand mathematical modeling, which in some sense is to describe a real-life system or a real-world problem by mathematical equations, to understand mathematical modeling, we give a simple example. So I have chosen one of the simplest examples of this type of models is called predator-prey models, and it is used to describe the evolution of two population species of two animals. So you see this little graph here, this X and Y. This will represent, as we'll see later, the populations of the two species. One is the predator and the other is the prey. And this type of systems that have only, for example, two variables, they can describe a complex system of nature, and this type of systems can go beyond and have vast applications. They can even describe epidemic models, as we will also going to see. Now, mathematical modeling is about finding the optimal way, so kind of to use the less possible variables to minimize the complexity of equations, and to fit as best as possible real data on the other hand. So minimizing complexity and maximizing how well they fit the real data. That is about mathematical modeling. And we're going to see this example of predator-prey systems. But before going to that, one comment is that when we have systems that evolve in time, the one way to what we are searching for to describe them is the rate of change of the variables, what is called the derivative of variables. So that is one of the key concepts of mathematics that are extremely useful here. And once we have found the equations, we have written down, then we apply our knowledge in mathematics and we try to understand them. We study them, and if we can solve them, we can solve them by hand, then we can have their full description. There are other cases when we have many variables and the systems are larger that we cannot predict analytically their solutions. In these cases, we use the computer and we simulate the equations of motion. But always we can have a qualitative behavior of how the system will evolve in time. Now, a comment before we go to the predator-prey system is that when we say about mathematical modeling, it's not only about systems that evolve in time. It is also about static structures in nature. We apply mathematics to efficiently describe what do we see: hidden patterns, symmetries, and self-similarity. So we use mathematics and we use formulas for efficiently describing a pattern that appears in nature. So how do we start? Suppose we want to model an ecosystem. We want to model how the populations of some species of animals change in time, and we want to express them with mathematics. We want to be able to predict how their populations will change in the future of the species, or for each of the species, and if it is a balanced or not ecosystem. So, first question is, how many species do we want to study? Here we see two variables, x and y. Suppose that, for example, x is the population of one species and y is the population of the second species. These populations might interact in the following way. X can be the population of rabbits, so it is the prey of the second species, that is the population of the foxes, that is y, and the foxes eat the rabbits, are predators, and the rabbits are their prey. That blue arrow here, so they kind of linked with this line segment, shows the interaction between the species, and it points towards the population of the predator. We might have more than two species. We might have three interacting populations. For example, plants, the rabbits, and Z is the population of the foxes. How do they interact? The first line segment has a direction, shows who is the predator of the plants, the rabbits, and the rabbits on the other hand are eaten by the foxes, so we have this arrow pointing towards Z. So here we have three populations linked in this way. We could have four interacting populations, and we could close that graph. Once we have fixed our variables and we know what we're going to study, the next step is to know how exactly our populations interact. What are the links between the species? This graph can be one choice, but it's not a unique choice. When we have four interacting populations, there can be many other choices. In fact, the number of choices is equal to the number of possible graphs. We can connect in a different way the variables to get different models. For example, here we have 3 predators and just 1 prey. X, W and Z now represent the populations of 3 species that are all of the 3 of them are predators, and their food are rabbits, for example. So we could have 2 preys and 2 predators, or we could have like now 3 predators and 1 prey, or we could have 3 preys and 1 predator. So think at this moment, how many graphs can you create with 4 interacting species? The next step is to model with mathematics these interactions and these variables, how do they change in time. So each one of the variables is a function of time, and when it is a function of time and changes in time, it defines a rate of change, and that rate of change is the key to model systems that evolve in time. Mathematically speaking, what we need is the derivative for each of those variables. For simplicity, let's think that we have only 2 interactive populations, like here, the rabbits and the foxes. So we want to write the equations that dictate their evolution in time. We want to write down the derivatives of these variables. Now, step by step, the reasoning is the following. These are 2 interacting populations, but let's think for a while. How would they do if they were on their own? So let's put here a barrier separating the 2 populations. The rabbits would populate and populate because they have no predators around. Their population would go up and up and up. Instead, the foxes would tend to extinct. Having no food will make them starve, and eventually they would die out. Now, if we remove the barrier and we allow these populations to interact, the foxes would eat the rabbits and their population would go up. Foxes benefit when being around rabbits, and the opposite holds for rabbits, who see their population going down. But when the foxes are too many, they don't have enough food, so they starve, and that causes their population to go down again. While the foxes are few, the rabbits found the chance to populate again and become more and more. So in principle, this ecosystem finds a very good balance between the 2 interacting populations. We want to write down the equations that determine their change. If they were isolated, the rate of change of the variable x would be something positive. That turns out to be proportional to the total population of the rabbits. On the other hand, the rate of change of the foxes is something negative. And the foxes starve without being around the rabbits. We have expressed their rates of change in time. We have found what is called the derivatives of these 2 variables. Now the big question is, when removing the barrier, what happens to these equations? How can we combine them? We want a link between the 2 equations. We want to add a term that depends on x and y. To link the variables, we can add something, a function that depends on both x and y. When foxes are around, the first equation should have some term that is negative. X and y are both positive, and minus xy is something that subtracts from the population of the rabbits, a negative term which decreases their population. What we subtract here will be added to the second one, to the population of the foxes. And that term is what actually links the 2 populations. It is a simple model that contains 2 variables, has minimal complexity, and it is the optimal way to describe the evolution of these two variables. And that is one part of mathematical modeling, describing with mathematics, with equation, in the easiest way, the optimal way, a system that in principle, this real life problem is very complex. And that is the elegance of mathematics. So the 3 steps in mathematical modeling is finding the variables, how many are they, what do they describe. Then second step is, if the system evolves in time, find the derivatives of the variables and write the equation that describes the dynamics of a system. The third step is to analyze the equation and perform a study that can be by reasoning in mathematics and writing explicitly solutions if that is possible, or by using the computer and simulating these equations, or doing both. One part that is analytically and treating a problem with a pen and a paper, or by programming in a computer, simulating the model and analyzing the outputs. Now, in particular, this system can be treated analytically because it is a quite simple model. Of course, when we go to many variables and to higher complexity, the computer is more necessary. So we will give different examples where we will consider different parameters and see how changing the parameters affects the system. So what kind of solutions do we get? Now here we have chosen these equations here. You can see that in front of x, the constant in front is 1, and in front of y, in the equation below, the constant is -1. The solution of this system is the following, shown in the graph here. You can see that the population of the rabbits goes up and down, like a periodic function, and the population of the foxes does exactly the same, just with a little shift in time. Okay, the two populations have the same maxima and the same minima. This ecosystem seems to be in a perfect balance. Let's change now the parameters. Now let's consider that the parameter in front of y in the second equation is -2, which means that the foxes tend to die faster. Then we get these solutions here. The rabbits with blue have higher peaks, and the foxes have lower peaks. Despite that, we have considered that the foxes now tend to extinct at a faster rate, the system is again in a very good balance. Just that the peak of the population of the foxes is half approximately of the peak of the population of the rabbits. Let's consider now that the rabbits populate twice faster as before, so that we have that 2 in front of x in this first equation. The coefficient now is double than before, and let's make the foxes have this -1/2 in front of y in the second equation, which means that their death rate now is much slower than before. So let's see if now this ecosystem finds a balance, and if yes, what kind of balance it finds. Since the foxes have a much lower death rate compared to all the other solutions, you can see that with the purple, their peaks in populations are now much higher compared to the peaks of the rabbits. However, the population of the foxes reaches very low values as well, so it has very low minima compared to previous cases, and moreover, the rabbits tend to extinct. The values of the blue lines nearly reach 0, which means that the population of rabbits is about to extinct. Although, because the population of the foxes reaches very low values, the rabbits find the strength to go up again and populate and survive. So that is, again, a balanced ecosystem, although both species are at risk, which means that if we slightly perturb this system by some, for example, external threat, the populations most probably will both extinct. So there are values of the system which make it very stable, that under external threats will go on in time and everybody will survive. But there are other values of the system that put the system at risk. And of course, one can go beyond and model the external threats by adding some further terms in the equations. And then one can study numerically or by theoretical reasoning and analytically deriving solutions, how can we make a system more stable and how much we are at risk. Evaluate the risk that we are and draw conclusions how to avoid such risks. Now, from predator-prey systems, I will make a big jump, and we stick to these equations, but we will change the scenario. Now, my x and y variables will represent something else. We will use them to describe an epidemic model that surprisingly has the same structure mathematically. So let's consider that a is equal to 0. Let's get rid of that term, which means that we have no birth at all in the x variable. The equation of the y variable is the same as before. Now we have added one more parameter, that is this epsilon, that is very small and is in front of the term xy that is included in both equations, and as we have said, it represents the interactions between two populations, and we consider that this is something very small. Now, why we're saying all this? Because we will try to understand what will be the evolution of x and y in time just by looking at the equations, which also shows how useful are the derivatives in predicting the future of a system. In epidemic models, this x variable will be the people that have not been yet infected by some infectious disease, and they can be infected. They have the potential to be infected. Y will be the population that is infected at the time t. The derivative of x is negative because it has that term minus epsilon xy. And since it is negative, it means that if we start by this blue dot on the axis, on the vertical axis, then that variable will be some curve that goes downwards and tends to vanish. It cannot increase because this derivative of the x variable is negative and can only decrease. The derivative of y, on the other hand, is a little bit of unknown. That derivative we want to determine whether it is positive or not. If it is positive, the purple curve will go up. If it is negative, it will go down. Suppose that this term initially is positive. It means that the purple curve increases in time. But this minus b plus epsilon x, there is always a competition between the variables and the constants. Epsilon is really small and x is going down in time. It decreases in time. So at some point, that term is expected to vanish. And after it vanishes, it will become negative. The derivative being negative means that eventually y will also vanish. So that yields this purple curve. So just by analyzing a bit the derivative, we can have a qualitative estimate of how the system will evolve in time. So without knowing anything about these equations and how we can solve them, we can have a qualitative prediction of what will happen in time. So even though we haven't solved the system, we can have a feeling, we can have an intuition how the system will evolve in time. The infected population will reach its peak, the maximum, when the derivative is equal to 0. So exactly when we have that x naught is equal to the fraction b over epsilon. Now, you will see some graphs that are produced by using the computer. Now, these curves, quantitative, take this shape here. And as we decrease and decrease epsilon, that interaction term, it means actually that we decrease the interaction between the infected population and the population that has not been infected yet. Now, decreasing further epsilon, which means that we decrease the interactions between these two populations, we get another curve for y that has a lower peak now. And the blue curve, the people that haven't been infected yet, tends a bit slower than before to 0. And what happens if we consider epsilon even smaller? We get this type of curves. The purple curve has a much lower peak, and it never actually intersects the blue curve. That means that its values, the y values, are always lower than the blue values. Actually, there is a part of the population that have never been infected, and they will never become infected because the infected population stabilized. So to conclude, this predator-prey type of systems can find a lot of applications in many different real-life problems, from ecosystems to epidemics and many other more. I hope you enjoyed this talk on mathematical modeling. Would be my last remark is that we were able to describe ecosystems and epidemic systems, that these are large systems and complex systems in principle, and by using only two variables, we are able to give a very efficient mathematical description of the problem by using models that are based on very simple assumptions. So thank you very much for attending my talk.
Okay, I think now sound is back. Thank you very much, Eleni, for this wonderful talk again. And also thank you very much to the members of public who were posting in the chat that the sound wasn't coming. We have now time for questions, which some already arrived in Padlet. Some I will read from a chart of YouTube, and basically I'll read the first question from Padlet, which quite mathematical question. So it tells, would be any benefit of making the interaction term plus xy or minus xy a function of the ratio between the predator-prey populations, like function of x over y?
Okay. Well, I have not thought about that. The idea when we have like these two interacting populations, one is the X variable, let's say that, let's fix that this is the prey, for example, and the other is the predator. Now, we could connect these variables with many different ways, actually. That was the simplest possible way. So how can we connect them? We can say that we have a minus in the first equation, minus a function that depends on x and y. And what we subtract from there, we will add it, that function in the second equation. Now, that function can be x over y. Now, I didn't understand the question if it's y over x or x over y. But it can be, of course, anything, but depends what would you like to estimate. So it depends on the model that you want to study. So I don't know, for example, now what would be the outcome of that, but there could be a model that would be, again, the predator-prey type that would have such an expression. So it depends of the data you collect. So once you have the data, you try to find the derivative. So if it's a mathematical question, we can say something more. You could try to model the dynamics of that. And if that is well fitted by a function that is x over y, then that will be it will work, that model. So in principle, yes, it could be any function that depends on x and y.
Thank you. There is also a question on a Padlet. Can this be used to model economics as well?
They use it in economics. They use it in many economical models. Now, I'm not an expert in economic models, but as far as I know, you can model in the banking system the deposit, that is the prey, the deposit of the bank, and the growth, the loan growth, on the other hand, it's the kind of, say, the predator. And by solving these equations, of course, it's a simplified model, but the bank can a little bit find solutions that can estimate the interest rates, for example. I think they could be also applied in companies that one represents the prey and the other the predator. So, of course, it has a lot of applications in economy.
Thank you. And now I read question from YouTube chat. Member Public JD asked, Helen, do you know of any books, puzzles or questions on mathematical modeling if we want to learn more or try it out?
I have to think and find the links. I cannot. There are brilliant books on mathematical modeling that we can share. Somehow I don't know, Andrei, if we can find the books and share the link maybe after the talk?
Yes, or basically we can post to people who registered email. Also, we can put this link to our blog, which describe about talk, and also in the chat on this YouTube channel. Yes, so we'll try to do that. I see also a question in Padlet. It says, how realistic these models of two animal species?
So if one wants to model two animal species populations, how they change in time, as I said in the talk, this is a simplified model. So it is based on very basic assumptions. Considers that, for example, the prey is considered to have a limitless appetite. So the prey, the rabbits, for example, can have as many carrots, let's say, as they want. So they kind of have infinite food. And the predator itself also has a limitless appetite, and so on. So it's a kind of not too realistic. and it doesn't take into account external factors. For example, of course, it's never a closed system, but what we can say is that from that point of view, mathematical modeling is interested in finding a minimal model that we can have control and understanding of the model. On the other hand, there are other models, more I would say they are computational models that can have a lot of parameters that can be very realistic, but they lose, on the other hand, on the understanding and controlling the system. So, for example, there can be models that are in a computer that we don't have equations for them. They are, let's say, equation-free, and they are. It is a program, essentially, an algorithm, a big algorithm containing thousands of parameters, and that such models are more realistic, but we lose that we don't have a control of the system. It is a code in a computer. We have to simulate and just see the output. So it can be also a mix of two. That is also something that we can have an algorithm that a part of that is a mathematical model equation-based like this one, and have a combination of that.
Thank you. I see there is a comment on Padlet where mentioned that this reminds me of rate equations in modeling of lasers. Maybe you can comment how, because from my perspective, it's also something can be found in chemical reactions and in varieties of kind of disciplines. So maybe you just can comment how you see this in various the mathematics.
Well, it is a predator-prey model. I don't know if it is a predator-prey type of model, but essentially physics, the whole of physics is a kind of trying to find a mathematical description and describing, I don't know, from astronomy to experimental physics. I mean, everything is based on trying to find an optimal formulation of the model, trying to model essentially the. So in that case, if it is a predator-prey type, I'm not sure.
I just wanted, because these lectures are also the main purpose of Bridge Science Week to inspire people to go and study various disciplines like mathematics. I thought maybe I can ask you how you kind of chosen mathematics for your study in your time. What inspired you to do mathematics, basically?
Personally, I loved the rigor of mathematics. That they go in a very logical sequence, mathematics, and I really liked that. I also was not good in literature, so it helped me. So in the beginning also of my studies, I studied pure mathematics, very pure maths, which actually I don't like saying pure applied maths, because there is no discrimination between mathematics. This is what I have realized. Just mathematics that might be applied, there's a high probability there will be applied mathematics, or pure mathematics. Usually we refer to algebra, but it can be that algebra is more applied sometimes than I don't know, than differential equations like Boolean algebra. Anyway, from my perspective, I liked very much the rigor of mathematics and the logical sequence. And I don't know, they are inspiring for me. One of the things I love in mathematics is fractals, for example, a lot. And we have a talk next week on fractals. That's a brilliant subject. Yeah, there's fascinating, many topics on mathematics that are very fascinating.
It's actually very interesting, this what you mentioned about pure versus applied mathematics. In particular, you come from country which are traditionally associated with like one of places where mathematics appeared in ancient times, and also philosophy appeared in ancient times, and then in modern days sometimes this discussion between pure and applied it really comes like two different things. But as you said, it's something which maybe was pure before, could become very applied, and there is no really kind of really such separation. Mathematics indeed like beautiful together, isn't it?
Yes, exactly. I totally agree with that. That we should not discriminate mathematics.
Right. So we just kind of our first lecture is approaching our 50 minutes time. If you still have some questions, you can still post them in a chat or in a Padlet. As Eleni mentioned, that there is a continuation of topics like fractals, for instance. Eleni just mentioned we will have a lecture just on fractals next week in mathematics. There are in total will be 6 talks on mathematics subjects and 6 talks on physics, but it's also the boundary is not really sharp. You will also find that very often boundaries between even these two disciplines are not kind of not there, and one kind of connects with another. With that, I would like to thank Eleni for this wonderful talk, and thank you for everyone who came to listen. I'll just mention that in just about 10 minutes, we have a second talk of this afternoon, which is on physics. And if you would like to join, you have a separate YouTube link in your email, which you receive from Eventbrite. You just can click there, and similar type of talk as you just have been here will be delivered after a short break. And thank you very much for coming for this our first talk of Lincoln Virtual this year, week of mathematics and physics. And see you in another talk soon.
Thank you very much. Bye.